Hi, Andreas. Welcome to the podcast, Everyday Metallurgy.
Hi, Peter. Great to see you there.
Thank you. We know each other very well because we are colleagues on a daily basis. And this episode is actually a takeover because many of the followers of the podcast has asked, what are you doing on your daily basis? You're only talking with people about what they do, but what are you doing? So therefore, today is a takeover where I will be the guest and you will take over the role as a host. So therefore, I will change to the Syntex shirt. I'm
Very
ready.
Good. I wish I had your red T-shirt to put on. I'm so glad that we could turn the tables, Peter. Very happy to take over this role. You and I, we work together. That's right. So maybe people, they know you. I'm a colleague. I'm responsible for business development. My name is Andreas, and I've been part of the Grundfos group for about 20 years. But in this specific discussion, I want to focus in on the work that you've done with the Honeycomb.
Yes.
So won't you tell us a little more about this Honeycomb, where this has come from?
Yeah. Back in 2011, we started a project where we wanted to produce filters. At that time, diesel particle filtration was hot because pollution was heavy. And there were a solution to make tape casting of a sheet, folded and welded together in a very complex structure. I wanted to change that to make it less complex, but still have the big surface areas you want in a filter. So therefore, I engaged with some students from the local university to look into a technology I'm calling metal powder extrusion. So extrusion is well known from the ceramic industry where honeycombs has been made for many years. But I wanted to transfer that technology to the metal world. And the first thing we did was we needed a machine to do it on. And Sintering is a very innovative company. So we don't just go out, spend money on machines like that. So I went to the local shop nearby and bought a Kenwood food machine, a meat grinder. And we made our first trials in that. And I'll just show you a video of the very first setup we made. You can see the machine here at the left. And you can see the materials coming out of the meat grinder. This first trial we ever made was made with a binder system called agar. And agar is protein taken out of seaweed. So the idea was we wanted to change the world by cleaning pollution from cars. And then you cannot use solvent material. You need to use material that are natural. So that was one of the innovative obstacles I put on the project. As you can see, some of it succeeded, some of it was a mess, and in fact, it was a problem for the meat grinder to do this task because the agar system, it has a glass phase is solidified at around 65 degrees C. So therefore, we needed to heat up to above 65 degrees. So we were running all this process at about 70 degrees. So therefore, we had heating elements on the meat grinder. And the meat grinder was not really made to run at this temperature. So it lasted for 3 days. But we got some very good results. I went to a conference, I presented it, and the feedback was great. People were very interested, not in the product, but in the technology. And we got in contact with some people who could help get us getting further, and we took it one step further. You can see here one of the first products we made, not really straight, but quite big, and you can see the first sign of what is it's not a honeycomb yet. It's it's just a pattern. But this was our first step, going from filters, because you all know the story about what happened with the diesel scandal. Nobody were at all interested in working with diesel cars, so the project was abandoned. And instead of that, we started to look into using it as a high temperature heat exchanger, a gas heat exchanger. So we looked into Inconel. So could you produce this material in Inconel material? It is possible, but the difficult part was to weld the end caps. How could you ensure that every second channel runs that way with hot gas and every second runs that way with the cold gas? Because we wanted to use it in a heat exchanger up to 800 degrees C. Then we took another leap and looked back into the automotive industry, where we combined these structures with a new alloy system that has been developed over the last 15, 20 years. It's called TWIP, twinning induced plasticity alloys. And when I went to school, that didn't exist. It was impossible to make alloys that both were high in strength and high in ductility. But TWIP broke what we call the banana, the material banana. All the material, they can either be soft and ductile or hard and high strength. But suddenly this TWIP alloy had the good thing from both worlds. So we tried to combine the TWIP properties with the design of such a system. Could you imagine making collapse zones in all this with a material that has a strength that is about 10 times higher than the aluminium used today in crash absorbers? That is a potential differentiator. But the big change came when we looked into higher temperature applications. We started with this heat exchanger, and we looked at the Inconel. But then a customer came and said, don't you have something very complex in shape that can run at very high temperature and you can blow gas through it? And I came with I think it was this part, and I put it on the table and said, something like this. Oh, is that possible? So we started a project to develop the technology, the metal powder extrusion technology, to a higher level, not to make it like that. So we found pretty easy, when you make parts this big, the difficult part is not necessarily the extrusion, but it is the sintering, which the reason for the company name Syntex is we are the sintering experts. So we started. You could see we could make the very nice structure, very thin walled material, because we needed the very thin wall to have a low resist or a high as possible resistivity, because when you want to heat it up, putting power to it, the resistivity, the more power you put into it, and the less in your cables. But sintering it often came out like that. So we have been optimizing and developing our sintering technology for a couple of years, and today this is a product almost 0.5 meter long, very precise in shape, and I think we have produced a little more than 10,000 of these over the last year. So today this is in full production as a heating element.
What a great story. But Peter, there's still some distance from being able to produce the monolith to actually making it into a heating element. How does that bit work?
Yeah, it's right. You need power to it. I have a little slide I'll share so you can see how it works. On this slide, you can see a little demonstrator of what we call the minimum viable product, the smallest unit of a heating system. If you look at the one to the right, the orange part is the monolith, and at top we have welded a bridge, and at the bottom we have connected it to the power. And when we put power to it, it starts to glow. But we are not just putting power to it, we are blowing air through the channels. And to give a demonstrator on how it works, I have a small video where you can see now it starts to raise and it starts to glow. This is speeded up. We typically say you can do this, you can heat up to a temperature around 1000 degrees of the gas outlet within 10 minutes. But comparing to other heating technologies where you have a lot of ceramic supporting it, you have a lot of delay in ramping up and cooling down. I have seen processes where it takes between 3 and 12 hours to heat up to temperatures similar to these. So it's a potential game changer in the heating business out there.
Very good. And Peter, can you explain something about the materials that you've chosen to work with?
Yes.
Well, what's now? What's next?
Yeah, the alloy we have on the material today, it's a FeCrAlloy. It's an alloy that is known in the world of heating elements. It's also the alloy we use in our sintering furnaces. So all our sintering furnaces are tube furnaces, where the tube itself is made in FeCrAlloy. So we have 27 years experience working with this alloy in our daily life. Therefore, we chose to run with that alloy in this product. The FeCrAlloy is an iron-based, but it contains high level of chromium and high level of aluminium. And what happens is that when you heat it up, the aluminium goes towards the surface and create a very stable oxide film. In our daily life, we are sintering at around 1200 degrees C in pure hydrogen atmosphere. And even when we have a very strong reducing atmosphere at elevated temperature, it's extremely difficult to remove the oxide film, to reduce it. So we know that this alloy is extremely stable, and we also have some tricks to make it a bit more stable in these reducing atmosphere that we have been struggling with for now 27 years. You could say the limit of this alloy is that in our furnaces, we are running around 1200 degrees. We know lifetime at that temperature due to creep is reduced to around 2 to 3 years. Then we have some movement, so it's just starting to sag. So therefore, we know that the alloy, when you want to use it at a heating element in industrial perspective, often customers, they demand 5 years of lifetime. So we know that you have to be below 1200. So we claim now 1150 is the number. 1150 degrees C is the max number you can run the heating element. We also make trials with this to heat up gas. And maybe that is the biggest differentiator of this technology compared to other electrical heating systems. When you have a standard heating element, it could be a rod. Then you want to heat a gas, and the gas comes in, it hits the surface, it's heated up, and it bounces off. But this gas molecule is not heated again until it hits the wall or hits the heating element again. It means that the activity of the surface versus the amount of gas you have to heat is extremely low. But in our case, we have a surface area inside because we blow the gas through the channels, and the surface area on the inside is 20 times higher than the outside. It means that just the surface area that is active to transfer heat is 20 times higher. But furthermore, when it comes on the surface, bounce off, it can bounce far away. But inside here, when it hits the wall and bounce off, it hits a wall again just after 3 millimeters, because that's the size of the channels. And that means in a system like this, it will bounce off ding, 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 ding many times. So the heat transfer, the power density of a system like this is up to 60 times higher than we have seen in traditional heating elements. And furthermore, because we have all these bounces and so many contacts through a very short distance, we have also seen that the temperature you can reach of the gas is pretty close to the temperature of the heating element. So we have been testing with a length where the honeycomb is 60 centimeter long, and the gas outlet temperature is only 100 degrees below the temperature of the element itself. That means if I'm running 1150 on the heating element, the gas temperature can be 1050. And that's a crazy number, because many of the people we have been talking to, they stop at 700 degrees. That's standard temperature you can reach with electrical heating when you need a high power amount. But you also ask what is next.
More. Yeah, well, I want to know what the limitations right now is 1100. What comes next?
Yeah, we are also looking into next generation materials, because heating elements can be made in other materials than the FeCrAlloy system. So we have alloy systems like Molybdenum Disilicide in the pipeline. It's very tricky to work with because it's easy to make, and it's reasonable to sinter. But then when you have to weld it, the Molybdenum Disilicide is a material that is a mix of a ceramic and a metal. So it's the mechanical properties are more like a ceramic. It's extremely fragile. But the electrical properties are like a metal. So it's conductive. But the difficult part is that when you have to weld to this very thin surface a connector or the bridge you saw before, because I want power in one end and I want the connection at the top. So I need to be able to make some assembly on it. And right now we are running with welding. But when welding, you should also choose a material that can run at the same temperature, because Molybdenum Disilicide can run up to 1500. Some claim 1700, but maybe a bit too high for this application. But if we say 1500, you also need to build the bridge in a similar alloy system. And welding these alloy system in such a thin shape, nobody has ever done that before. So that is next level of difficulties. But if we succeed, we will be able to deliver gas heated up to 1300, 1400 degree, which opens up for several new industrial processes that today are only dependent on coal burners. And that can be a game changer in the in lowering carbon emission for these hard to abate industries.
That's a great application or a great explanation. And also I can see your confidence in being able to come up to these higher temperatures. Are there other limitations that we're facing or other things that you think this is actually a barrier that needs to be overcome with the current design?
Yes, we're looking into stabilizing it further. And one of the things we have seen, one of the applications that I'm really looking into and that I hope will be a big one for this technology is the hydrogen DRI. So reduction of iron oxide pellets with hydrogen. But the hydrogen has to be preheated to be reductive. And when you preheat the hydrogen, you have to heat it up to around 950 degrees C to be reactive enough to reduce it and to be speedy enough to make it industrial interesting. Then when the hydrogen has passed over, it is turned into water and iron, but there's still hydrogen remaining. So you'll make a loop and take the outlet gas from that process back into a condenser, remove the water, and bring in the remaining hydrogen. But very often in your iron ore, there are also some residues of carbon. And when you put hydrogen into that system, you have lack of oxygen. And the gas coming out is typically carbon monoxide. And carbon monoxide coming back, it is not condensed out. It will go back into the system. It will be preheated. And in the preheater, when you have extremely pure hydrogen at very high temperature, reducing atmosphere, you will break the protective surface of the oxide film that I talked about previously. And when you open that and you have access directly to the metal and not the oxide, the carbon monoxide, oh, suddenly I can see the chromium, and it will attack the chromium. And what happens when carbon monoxide reacts with chromium is that it forms chromium carbides. Well, chromium carbides doesn't harm anybody. No, but this disadvantage is that chromium carbide has a density only half of the chromium itself. So it expands. And when it expands, it breaks. So it forms dust. And it is so aggressive that the material just falls out. And that is called metal dusting. And metal dusting is one of the worst failure modes you can have on high temperature heating elements. And it is pretty known in reducing atmosphere. We have seen several attacks in our furnaces over the years we have been sintering. So it is a failure mode that we are familiar with. But the advantage of this technology is that with this low delta T, the low difference in the gas temperature outlet and the heating element temperature, if you can reduce that to only 100 degrees, that means that you can run the heating element at 1050 and still deliver your gas temperature 950. And at a temperature 1050, your oxide film is so strong, it will not be reduced. So this way of heating is a life elongator of heating elements running in hydrogen. That is our belief.
Great explanation. Thank you, Peter. You mentioned other gases. Are there any limits to the types of gases that we can use the heating element for?
Not today, not what I know of. If we can solve the problem with hydrogen, everything should be possible. I think the biggest risk is if the system is leaking, not the honeycomb itself, but the entire system. Then you have gases all over. But that's not the honeycomb problem. That's the housing problem, or the pump, or the piping. So I don't see any gases that cannot be heated with the honeycomb heater.
Okay. In your diagram, you also showed a cold end and a hot end. The cold end is ambient, or what's the inlet temperature? Is that a limitation as well?
Yes, it is. We have designed it. The cold end is where we have the connection of the power. We are today trying to design the connection very robust, working with high temperature alloys there as well. Because we're looking into some applications where inlet temperature of the gas itself is 500 degrees C. So if we are not able to connect in 500 degrees C, we are not in business. So it is a difficult task. It's not a walk in the park, because the connection themselves, when you make them in high temperature alloys do not have the same conductivity as copper. So therefore, you also have heat in themselves. So you're just removing the heat point a little down. The advantage is that we purge the gas all over the system. So we have the inlet gas also hits the connector system. So even if you have losses, electrical losses, power loss in your connector legs, well, it is just heating up the gas. So we have preheated the gas, but that just increases the efficiency. So compared to other technologies where losses, they are outside the system. These losses are in the system, so they are not losses system-wise, and therefore efficiency is pretty high compared to other. If we compare with hydrogen burners, it has been very popular in academic societies to look at hydrogen burners to substitute natural gas burners. But to produce hydrogen, efficiency in the production of hydrogen is often around 50, maybe 60%. So you have a loss on half of your energy there. And then again, in your burner, you don't have 100% efficiency. So the sum of the efficiency of a hydrogen-based system transferring electrical power to heat is often below 50%. Where I expect in a system like this, efficiency is above 95%. Of course, you need a power supply that's high quality. Don't buy something cheap on Alibaba that heats it itself up. But it's a big differentiator.
Very good. And Peter, you mentioned the power supplies. How big can you go? Can this scale? Is there? I mean, a single honeycomb. What kind of power effect does that have?
Yeah, the one I showed you on the video that was heating up was 2 of these. So the volume those two next to each other is around a liter. And in that, we are able to transfer above 30 kilowatt of electrical power to heat up the gas. But then we can put these U-shapes in serial next to each other, so we can build a larger array. And a design where we add, I don't remember the number, how many we have to cluster, but we made a concept where we build a system that can deliver 1 megawatt, and the dimensions of that is something like 400 times 400 millimeter, and then 450 millimeter high. So in daily words, that's a large case of beer. Then everybody understands the size of it.
Very good. Peter, now you're a metallurgist, and I think I can see that you are excited about the materials, the characteristics of the properties of what you are producing. Where can it be used? Try and tell me more about what are the applications for this? Where will I actually see a use for this?
Mm-hmm. My favorite is the steel industry.
Why?
Because I'm born out of steel. I'm a steel man. And in the steel world, you have two core applications. You have what we call the upstream, where you take the iron ore. So that's the mining metallurgy part of it. When you have mined the ore and you have made pellets out of it, you have to reduce these pellets. Today, the majority of reduction occurs in blast furnaces. Blast furnace is coal, pellet, coal, pellet. So that is a carbon emission machine. That process itself is responsible for 7% of the global emission of CO2. But in that process itself, you also blow in hot air at the bottom to start the process burning. That hot air is produced with gas burners or coal burners today. That could be a brownfield, a replacement of a system if we heated up the air with a honeycomb. But the game changer would be the DRI, the one I talked about previously, where the blast furnace are removed. You don't use coal, but you use hydrogen. In first level of DRI, it is cracked natural gas that forms syngas, and the syngas is a reducing gas. But the syngas can also be produced in these guys. So that's the core area where I see the use of it in the upstream. But in downstream, if you look at downstream, there's a lot of heating and heat treatment, drying, and many of these processes, they occur in the temperature window between 700 and 1100 degrees C. Preheating before rolling. So when you have a slab, you need to preheat that. That is done in furnaces bigger than my house with gas burners today. So there's an extremely large gas consumption in the downstream just of a steelwork. But then you could also look into other areas. So foundries, there are a lot of gas burners as well there. Aluminium, something as stupid as preheating the ladle or the ton dish in the aluminium industry today is done with a gas burner. And when you burn with a gas flame, you produce a lot of CO2, but in fact you produce even more water and the water is blown down on the surface of the tundish dish, and an equilibrium between the tundish dish and the gas flame is created. So there's water in the ceramic. Then when you purge your liquid aluminium on top of it, it flows, and the solubility of water in liquid aluminium is very high. So it will just go out of the ceramic and into the aluminium. But then when it solidifies in your casting process or in your die, the solubility of water in solid aluminium is almost zero. So could you imagine where it will go, that water? It will react with the aluminium. And water contains hydrogen and oxygen. The oxygen loves to create aluminium oxide, but then your remaining part is hydrogen. So very often it's seen that you have hydrogen blisters in aluminium casting products due to preheating with a gas burner. That could just such a simple failure could be removed by preheating with a system like this. So you're not only saving the CO2 away from the gas burner, you're also making your process and your product more stable and higher quality.
Very good.
Yeah,
that's a lot. Yeah. Anything else there?
I have one more because we have also been playing with this technology as an afterburner. In many processes today, you have volatile molecules that comes out, and volatile molecules are organic compounds that are smelling pretty bad, or they are dangerous to the human health. So you're not allowed to put them out into nature. You have to burn them prior to putting them in your exhaust system. And burning of VOC, as they are called, typically occurs around 800 degrees in furnaces this size, 2 meters in diameter, several meters long. The residual time of the gas into the furnace system is, by rule of thumb, between 1 and 2 seconds. Then we made a trial with these. We took the gas, the exhaust, and we blew it through the honeycomb, and we calculated with the gas flow we had, residual time was something like 10 milliseconds. So 100 times less than the rule of thumb says you need to make it work. But because the distance to the surface where activation occurs is so little, we have shown that we can make the same process into the honeycomb, that it requires a chamber the size of a room, or 50 cases of beer to do under normal condition. And again, that is not only space saving, it's also a way to transfer from gas burners to electrical power. And when doing that, in fact, we have also made some calculations that you are able to recycle. Because when you burn with a gas burner, you cannot recycle the air, because the air is, you have burned the oxygen. You cannot burn the oxygen twice. But we don't have anything burning here but the VOC itself. But the amount of VOC is not high enough to remove all the oxygen. So by recycling, we have calculated that we can reduce the energy consumption of an afterburner system with 40%. So not only transferring from gas burners, but also reducing the energy consumption.
Which has OPEX benefits.
I guess. Yeah.
That's great.
Now,
That's
I don't
wonderful, Peter. Peter, just a question. Where are you? Say something about the location.
Yeah, I'm in our Honeycomb lab. So we have built a lab facility where we can test it. So behind me is our test facility. We have installed 70 kilowatt of power in the house. It gets pretty hot in the room when we do that. And then we have also meeting facilities, because we would love to invite guests and potential customers to come make tests with us. We had a very funny experience. I shared some data with a potential customer, and he said, "Oh, Peter, something is wrong. That data doesn't. I think you made a mistake, because you wrote that the flow rate was in liter per second. Don't you mean liter per minute?" Because he thought this factor of 60 was impossible to reach. And we had emails back and forth, and I was not able to convince him that it was liter per second. So we invited them to come play with us in the lab and make tests with us. And we spent 2 days in the lab. And after that, he said, "Wow, the learning of what we did today just saved half a year, because I wanted to bring this home, and I wanted to test this and that. But these 2 days, I am convinced I don't need to make those tests. Let's skip that and jump into talking business."
It's easier when you can actually see it with your own eyes.
Yep.
Peter, this was a great opportunity for you actually to be on the other side of the microphone. Normally, you're the one doing the interviewing, and we've managed to turn the tables. Yeah. Is there anything else that you want to add? Something that I haven't asked about?
No, I feel so some of my guests say, "Oh, I'm nervous." And I say, no reason for that. But now I know, because I can feel it too.
There you go. Yeah. Well, I think you did a wonderful job again explaining what you work with, explaining your passion, explaining the potential of what you're working with. So thank you for sharing all of this. Where can people go if they want to hear a little more?
We have a Sintering Honeycomb homepage. So go to Google, right, Sintering Honeycomb, then it will show up. We also have a LinkedIn page where we share some of the stories from old days until today. Mm-hmm. So please take a look there. And then we are also participating in conferences. And Andreas, you and I will go to Aachen very soon to share some of our findings there. So please feel welcome to join us.
Very good. Peter, thank you so much. Thanks for sharing, and I look forward to seeing the questions that come in the description underneath. Add comments, add questions, and then I'll ask Peter to address them afterwards.
Wonderful.
Very good.
Yeah. Maybe I should wear that again now.
There, you can put that back on.
Yeah.
Thank you so much, Peter.
Thank you. I really enjoyed it.
Very good. Thank you. Bye.
Bye.